Hello everyone. In this video we are going to look at static and dynamic balancing of rotary masses. Here first we look at a scenario where all of these masses are on the same plane. Okay, so like you have one shaft, and on this shaft that is mounted on two bearings here and here, there is only one gear, one basically disc, one object rotating at one single place, and balancing this is quite easy. So here, instead of one solid object, I represented it by three individual masses or weights, W1, W2, and W3, which are off-center at radial distances of R1, R2, R3, and their angles with respect to some x-axis and y-axis that are attached to the frame are theta 1, theta 2, and theta 3. So this XY frame is, you can say this one is attached to the object and is spinning with it. Now, we're going to look at the static case where nothing is spinning, and we're going to look at dynamics case where everything is spinning with angular velocity omega. Our goal is to put one single weight or mass, WE, at location RE with relative angle theta E such that the single mass would cancel the effects of all these other masses, both for static and dynamic scenarios. So, how do we do that? For a static scenario, all you need is basically that the total moment of these forces with respect to the z-axis to be zero. Okay, so what you need, if I go back and do a little bit cleaning, so what are the moments here? Well, what you have is basically this W that you have down here. A W is going to create a moment for this z-axis, and that is what? That is W times this distance, and this distance, if you look at it, that is R1 cosine of theta 1. And the other angles are R2 cosine theta 2, R3 cosine theta 3, and RE cosine theta E. So sum of these W's times their R's times their cosine of the angles should be equal to what? Should be equal to 0, and this is exactly what we have down here. And well, actually this is moment. Let me clean it. This is some moment, and that is about the z-axis, really. Okay, that's not Fy. It's moment z. So this is the equation I need, equation 1. This is the equation that if you satisfy it, statically the system is going to be in good condition. Now, of course, you're going to have forces at the bearings. You might say it doesn't look like it is statically stable. Why? Because each one of them has some W, right? Each one of them has some W, and they're all downward, so there should be something upward to cancel these. That's right. There is a reaction here and a reaction here at these bearings. Some of those two should cancel these forces. So those bearings are to bear radial loads. Okay, but here we just want to make sure that the system does not start spinning as a result of these masses being at different radial distances with respect to the center. Now, what about dynamic scenario where everything, as I said, is spinning now with angular velocity omega? What condition do you need now? Well, in this case, we'll look at what? We'll look at the centrifugal force, or equivalent to that centripetal force, right? And for simplicity, we use centrifugal. You know, centrifugal is not a physical force, it's an imaginary force, but it's equal to centripetal, it's just in the opposite direction. So whichever one I use, it's not going to affect the final equations. So the centrifugal force for this mass or weight W2 which is a radial distance r, is going to be radially outward like that, and the magnitude of it is m, which is W2 over g, right? M times what? Times the radius, which is r2, and then times what? Times this omega squared. So it is going to be like this. Let me move it a little bit. So this is what? This is that centrifugal force corresponding to the spinning mass or weight M2 or W2. And there is one here for W3. There is one here for W1, and there is one here for WE. And these forces should balance each other. So if we decompose them along X and along Y, some of those should be equal to what? 0. So that's what we have down here. We decompose those centrifugal forces along X and Y. For X, we're going to have cosine theta. For Y, we're going to have sine of the angles. And if you set them equal to 0, what you can do is you can get rid of these omega squared from both sides of the equation, since the right-hand sides are 0, and you get the required equations 2 and 3. So if 2 and 3 are satisfied, then I have dynamic stability. Now, one thing you need to pay attention to is if you look at equation 2, that's the same as equation 1. So if I can have dynamic stability and balance 2 and 3, 1 is automatically satisfied too. So dynamic balance here guarantees what? Static balance as well. Okay? And I mentioned that for you over here. Now, we really have two equations to satisfy, 2 and 3. And how many parameters can we choose? Well, you can choose this mass of the ME, you can choose the radial distance of that, and you can choose the angle of that. So ideally, it seems like you have 3 parameters to choose and 2 equations to satisfy it. So it seems like you have more equations than you really need. But let's take a look at these 2 equations and analyze it one more time. So here, if I have the numbers for WEs, for WIs, RIs, and theta i's, if I have these numbers as I have in this example, so here for the same figure that I showed you, I gave you some numbers. W's are W1 like 2, this next one is 5, the next one is 3, and theta i's are like 30, 80, 160 degrees, and the r's are 4, 5, and 3 inches. So if I give you these numbers, right, and here this other column, if you want, it could be I really, right? So this is your I, which is 1, 2, and 3. Then what kind of equations would we get? Let's take a look. So here I'm going to apply these equations 2 and 3, which you can see down here. And this summation that you have over the given masses, these are numbers. If you plug in the numbers, W's, thetas, and R's, you can find that this summation whole thing here is going to be 2.818, and this other summation is going to be 31.703. So now I have the first equation is WE, negative WE, 3.5, and let's say this 3.5 I don't have. This 3.5 I picked a distance for RE. Let's say it's just RE. Okay, so let's say it's just RE, and the same here, it's just RE. We didn't pick any value for it. So these are the 2 equations that I have, these 2. If I divide the 2 equations, so I'm going to divide them, so I get rid of W's and R's, right? And I can divide the bottom one by the top one, right? So I get tangent of theta, or I can use 810.2 to get an accurate value for theta e, because it's important in which quadrant this theta e is. So if you want to be accurate, you should not use arctangent. You should use what? Arctangent 2. So from there, if I use arctangent 2 and get the sine and the cosine of theta e from these two equations, which are these two numbers, then you'll see that both sines and cosines are going to be negative because w is a positive number. So both of them are going to be negative, and when both sine and cosine are negative, you are in the fourth quadrant. So your angle has to be what? In the third quadrant. So the angle is going to be in the third quadrant because both sine and cosine are negative. So your angle should be between 180 and 270, and you see here the angle calculated is 264.9 degrees, okay? So this is your angle, right? I got the angle. Now let's go back and see how we can solve for WE and what for the RE. So if I plug these numbers back, I get one number for cosine, I get one number for sine, and then what? So I get some number here, okay? And I get some number here. So now I have WE times 3.5 times this number equals this, and WE times 3.5, the same number, or RE in general, RE times the sine equals the other number. Now, are they two different equations? No. They should be the same equation, right? Because both of them will give us the product of WE by what? RE. So although they look like they are two separate equations now, they are not. You can only use one of them. So if we use either one, all you can calculate is simply what? WE times RE. You can only calculate this guy here. You can find that. Okay, and now if you can find that, you have one number and two unknowns, one equation and two unknowns. So you have to pick one of these, right? You have to pick one of them. And here in this problem, we chose RE. We say this one we know, and then we can solve for what? For WE, which in this case is 9.15 pounds. So if you put the mass of 9.15 pound masses, if you put that mass at angle 264.9 with respect to the current x-axis and at a radial distance of 3.5 inches, that should dynamically and statically balance what? All these three other weights, and your system is in balance. Okay, so this is the scenario where you have what? You have all objects, all masses, all rotary objects on the same plane, in this case on the xy plane. Okay, and three parameters to choose, but you have two equations, so typically you pick one of them, and most of the time you might want to go for RE. Now what happens if the masses are not on the same plane? They are not coplanar, which happens most of the times. So you have like several discs or several gears on a shaft that is fixed at two bearings C and D. And here, let's say you still have like three masses or three gears or anything. And here you want to, again, make sure you have a static and dynamic balance. So here we're going to use two masses instead of one. We put WA and WB. Why? I'll show you in a second. And for each one, we pick their own radial distance as well as their own angles. And then here, everything has an axial distance from one of the bearings. So in this case, A represents the distance from each one of these masses or weights from what? From bearing C. So A1, A2, A3, AA, and AB. So each weight or mass, a balancing one, has also some extra A. These are under our control. These AA and AB is what we pick. But A1, A2, A3 are given to us as a part of the problem. So here, if we want to make sure the system is balanced for a static scenario, again, the equation is exactly similar to this top one, no difference. Again, we need to make sure sum of the moment about the z-axis is equal to 0. And this is that equation that you have down here, and I just fixed that. That's not Fy, that's Mz. And here you have two unknowns, this one and this one, two sets. This side here, this one is entirely given. Okay? Now, where would you put this plane xy here? You can put it anywhere you want along this shaft. Many times people choose to put it on one of these W1, W2, or W3 planes. Okay? So basically they pick this distance AA to be equal to A1, A2, or A3, and they do a similar thing for WB as well. So they pick their WB to also be on the same plane with one of these other masses. Okay, but these two are under your control. And the reason you pick AA and AB as the same as A1, A2, A3, because you want to attach these small masses onto the already existing what? Discs or gears. You don't want to separately add another mass off balance with respect to the shaft. So these AA and AB, as I said, are typically chosen to be equal to like A1, A2, or A3, and we don't typically choose separate distances other than those, because then we have to attach those balancing masses with some rod, with something to the what? To the shaft. Okay? So this is the static equation. Now let's look at dynamic. In dynamic scenario, it's a little bit more interesting. Why? Because here, this is this mass that I put in this location, W at radial distance r angle theta, and this F here is the centrifugal force corresponding to it. So that is W over G times what? Times basically R times omega squared, okay? Where this one is spinning with angular velocity omega, and this radial distance is R. So, what's happening here? Not only that centrifugal force has two components, one is this, F sine theta, and the other one is this, F cosine theta, that the balancing masses MA and AB have to cancel. Also, since these two forces are applied at a distance A from this bearing here, those forces with respect to that, the axis of this bearing, X and Y, can create moments. This vertical force F sine theta will create a moment about x-axis, which is equal to F sine theta times A. And this horizontal force, which is in a skew situation with the y-axis, will create a moment about y-axis, and that is F cosine theta times A, as seems like I have another thing that needs to be fixed. It has FA times cosine theta here. Okay? So not only you have to make some fx and some fy equal 0, also on one selected plane, you need to make sure that what? Total mass x and total mass y also equal to 0, because if you don't, then basically in order to cancel those, you need to have these big bearing forces. And if you apply a lot of big forces on the bearings, you know, the bearings start to break over time and you reduce the useful life for the bearing. So you have to make sure that you reduce these required bearing loads to cancel the moments as much as possible by proper dynamic balancing. So here, why can't I just pick one mass, WA, at a distance AA, angle theta A, and radial distance RA, and that does the job of balancing for me. Why can't I not just go with a single mass? Well, let's take a look. So what equations did we want for dynamic stability? One is total force in the xy plane along x and y equals 0. The other one is if this xy plane is placed at bearing C, then total moments of these forces for x-axis and y-axis also equals 0. So these are those 4 equations that you need to satisfy now. Okay, where you can see that here the m times r omega squared, this is your F force. These 3 will form the F force that you had in this picture above. That's your F force, and you have your A here, and you have your sine theta. So it's exactly this formula. And similarly for the bottom one, you have cosine theta. Now, I need to satisfy all equations from 5 to 8, and how many parameters do I have to choose? You might say, well, you have 4 parameters. You have theta A, you have RA, you have WA, and you have AA. You have 4 parameters and 4 equations, so you should be able to go with just a single mass. Can I? Let's take a look, see if I can. So, let's say the numbers for the 3 W's and 3 R's and 3 thetas and the 3 A's are all given. So let's say all of this information in blue that I underlined, let's say they are all given to me. Okay? Yeah? Can I satisfy all the 4 equations? Well, let's find out. So, if I plug in the numbers, I get a number for this whole thing. This is going to be a number, this is going to be a number, this is going to be a number, and this is going to be a number, right? I get 4 numbers for them. Different numbers, of course, right? Because in the bottom ones, the A's are involved in the summations and multiplied before adding summations. So this number here is clearly different from this number, because the top one does not have A's, the bottom one does have A's. Okay? Yeah? So now what happens? From this one, I get what? From this one, I get that. This term here, this term that, if I can highlight for you, yeah, sometimes you're going to have a hard time. This one. This term is going to be some number, whatever it is. Let's just call it C1. Yes? In the bottom equation 8, this guy here is going to be what? Is going to be some number, let's say C underscore 4. Yes? C1 and C4 are not, how are these numbers related? If I divide these two, what do I get from these two? If I divide the bottom one by the top one, everything gonna go except for AA. AA is the only thing that stays, and so it is gonna be C4 over C1. Yes? So from here, I can get what? I can get AA, right? That's what I get for AA. Fine. Let's move on. So I got AA covered. This one is good. Now, if I go to the next 2 equations, these 2, here, I get what? From here, I get this ratio is equal to this, this product is equal to some number called C2, yes? And then from 7, if I go for it, I get what? This guy here is equal to C3, where C3 is basically C2 and C3 are these ones. This summation and this summation. Right? Now, let me do something. So if I divide, as I said, if I divide the bottom one by the top one, you get this result. But if I divide this third one by the second one, what happens? Yes, you're right. The result is still RA because everything else is similar. Okay, so if I do that, then AA has to be what? AA has to be C3 over C2. Now, which one? You see, I get two different solutions for AA, and these two are not necessarily equal. These two ratios are not equal. They are not related to each other. I can easily pick my A's, R's, Omegas, and thetas and M's or W's so that these ratios are not equal. So you see, I get two different solutions, and that cannot be. Because it cannot be, that means I cannot satisfy these equations all at the same time with only one single mass MA, which is at an unknown RA, theta A, and AA. Okay, so these four equations cannot be satisfied with a single mass. Therefore, I need to have what? I need to have two masses, as I showed you in this picture. I need to have two masses, WA and what? WB. If that's the case, your equation becomes these guys that you can see, 9, 10, 11, and 12, which is just like 5, 6, 7, and 8, but a term for B is also added. Okay? Now you're going to have a bunch of more parameters. And how many parameters do you have here? You have 8 parameters. Why? Because each mass comes with its own radius and comes with its own angle and distance. Right? So here, as you can see, you have 8 parameters in blue to choose, but 4 equations. And in order to satisfy it, we have to pick 4 of these parameters. As I said, for the A's, the selection is limited. Why? Because we want to attach these masses, WA and WB, to one of these rotary objects. So we typically, as I said, pick, let's say what? Pick AA to be the same as A2. So put this guy right here. And then maybe WB, attach it to W1. So put WB right here. Okay, that will take care of the A's for these two objects. That will take care of the A's. We don't want to add more shafts to the to your rotating object. So these A's are decided. So now I'm only down to 6 parameters. And just like previous case that I showed you, we pick R. Remember last time we picked R. This time we do a similar thing. We pick the R's by ourselves. We choose how far on this discs, right? Because now you're going to attach it to the same disk that has W1. So this W1 is like a disk, which is now represented by just one single off-balance mass. So now, if you attach your balancing mass to this object here, you're going to put it somewhere on this disk, right? Then this distance here, this one, this R, is basically based on where you attach it, magnetically or anyway, that R is also taken care of. So that R, you cannot choose whatever you want. It has to be limited to the size of what? This disk or gear. That you have a W2 for WA and the one for W1 for WB. So this picture here is wrong the way it is shown. You cannot extend your gear so you attach that mass. Okay, if you want to attach WB to the location W1, you better what? You better bring it in. Okay, if that radius represents the radius of the disk, it might not. Okay, so you might put it down there. These two R's are taken care of. You're only down to 2 angles and 2 masses. And guess what? Just like previous time that you had 2 equations and two unknowns, mass and theta, and you found it. Now you have four equations and four unknowns, and again the unknowns are these masses or W's as well as what? Their angles. And I assume everybody, once you know these numbers, should be able to what? Solve for four equations and four unknowns. So this is the overall process of what? Balancing. This is the theory behind balancing rotary masses. Hopefully it was useful to you. Before I finish the video, I need to mention that just like my previous video, the pictures and the equations here are taken from the book by Martin, which is Kinematics and Dynamics of Machines. That is an amazing textbook, and I have added it to the list of my references. And I want to tell you that I modified some of these pictures and some of these equations. So the original pictures are from him, but I modified some pictures and I modified some of the equations to make more sense, but they are all accurate. Okay, thank you so much. I'll see you in the next lecture. Thanks.